Okay, good morning, everybody. I It's 5:30 in the morning. I'm in a hotel in Denver, and I found the most private place I could to do this recording. Um, but there's a little jazz going on in the background. But as I emailed out, we're going to switch up the syllabus just a touch, and I'm going to do one pretty important example related to this. Fatigue loading in bolts. And so this is kind of a fun example that I found, and it relates to we have these two parts here getting pulled apart, and the force is going to go from 0 to F max. We don't know what F max is going to be yet. So this is what I'm really interested in here, and we're going to do a couple different ways. The first way we're going to do it is not preload this at all. Just get it snug, and then go from 0 to F max, and then figure out, find the maximum F, but we want to go for infinite life. And so let's do that part first, and then we'll discuss. All right. So if there's no pretension in this thing at all, that means that little force diagram that we did the other day looks something like this. And as you recall, I don't want to get rid of that. This was our external load P, and this was some other force F. All right. Remember, we had initial pretension down here, right? But it was up here. But if the pretension is 0, it goes like this. Well, there's no compressive load at all to give up, so all of my load winds up looking like this. So I start down here in the corner, and I just load this thing up like this, right? Get out here. So the force in my bolt winds up being all of this, and my compressive load is 0 the whole time, right? Well, okay, we still have to figure out what the max load is. So I'm going to go from loaded to unloaded, loaded to unloaded, loaded to unloaded. So in other words, this whole distance here winds up being P, right? So, if I make a sketch of that, it looks a little bit like this, right? Which you saw in the exam, if I plot time versus force. And so I got to figure out how to get, there we go. And so my mean force is my force over 2, and my alternating force equals, what is that? Well, that's also F over 2, right? And so that my alternating stress winds up being, let's see, the mean force divided by 2 over the area times some fatigue factor, right? And then my alternating mean, or my mean force, my mean stress winds up being the same thing. Well, I look up in the tables. So look in table, I find that the area for this particular bolt is 0.1419. 0.1419 inches squared. Okay. And let's see, what else can I look up? In table 810, I can find that the proof strength equals 85 KSI. I don't know if I'm going to need that yet. And then the ultimate strength equals 120 KSI. And from table 817, what do I find there? That it gives me the endurance limit equals 18.6 KSI. Now, it's important to notice that this includes, I'm going to make a big arrow there, this includes the KF for rolled threads, which are by far the most common. Right, so we're not going to double dip here. We're not going to use the KF here as well as the KF here. So we're just going to use the endurance strength. Okay, so I want to have a safety factor. Where's my mouse here? Okay, so for a safety factor of 1, what do I want? I know that my stress, the equation looks something like stress alternating over SE plus the stress mean over the SU has to equal 1, right? So I can plug all my stuff in, and that means I've got F over 2A over SE plus the mean is the same because it's that, you know, the sine wave that's just sitting on the axis, F over 2A here over SU equals 1. Now let's see, what do I know here? I can go to green. I used to know how to change color. Green, I know the area, I know the area, I know this, I know this. The only thing I don't know is my force. So I can solve that. This gives me F equals 4,570 pounds. I don't know if it's just me, but the jazz in here seems to be getting louder. Okay, so we know that a 1/2-inch bolt, I brought one into class the other day, a 1/2-inch bolt is good for about 12,000 pounds. But due to the stress concentrations and the endurance limit and fatigue, it drops me down to 4,570 pounds. Okay, so this is really important to note because we're going to do it again with a pretension. Okay, so here we go. We know that without preload, we were at 4,570 pound force. Okay, but now what if we do add some preload to this? What exactly changes? The key thing that changes is this little picture here. Remember that we've got some initial tension. Let's get rid of this for now. We're going to plot force against the external load again. But this time we've got some initial tension, and we're going to preload it up here. We also know that the bolt is not nearly as stiff as the members, and so it looks a little bit like this. Now I've got the force in the bolt up here, and then the clamped force in the members down here. So as I pull in, you know, pull release on these rings or whatever this thing is, that force is picked up here. So this is P. However, I can draw this dotted line that goes something like this. So then the good news for us is that the fraction of the load, I'll put that in green because that's good news. The fraction of the load picked up by the bolt is actually pretty small. This is the load borne by the bolt, and then the some other color, because it's not really bad news, but it warrants a different color. I'll do it in blue. Goes down here. This is the reduction in clamping force, so we'll call that reduced clamping force. Okay, well, the big question is, what's the fraction of this over this? It turns out PB, so the fraction that the bolt picks up versus the total load is how stiff is this relative to everything else. So that's the stiffness of the bolt relative to the entire stiffness of the system, which is the stiffness of the bolt plus the stiffness of the clamped members. Okay, but we know that the stiffness is related to AE over L, right? We've done a problem like that in class. So it's the bigger the bolt, the stiffer the bolt. The stiffer it is, the longer it is, the stretchier it gets. So that's for the bolt. And then it's AE over L for the bolt down here, plus AE over L for the members, right? Well, if we look at this, the effective length of the bolt is the same as the members, so it seems like we can cancel a bunch of stuff out there. And it's all steel, so I can cancel all that stuff out. The lengths I'll cancel out. And so really my ratio of stiffnesses becomes the fraction of the load that this picks up winds up being, what does that work out to be? Oh, it's the ratio of the areas. It's the area of the bolt over the area of the members, the clamp members. Remember, this is the area of that frustum, and then plus the area of the bolt. Okay, and so I'm going to make an important note here in the interest of time and everything else. For the area of the clamped members, I'm going to use the juvenile method of equivalent equivalent diameter. Okay, so that's really important to make note of this here. That gets a big blue box. All right. So let's go get some work done now. If I were to, let's see, can I zoom in on this? Whoa, that was too much. So I'll work up here a little bit. What color am I working with? Black. So it turns out that the area of the bolt relative to the area of the bolt plus the area of the members equals 0.14. Right? Now this is really, really important. This gets a big green box because so my bolt only picks up 14% of the load, right? That's great news for me. So you know, if I load, unload, load, unload, load, unload, only 14% of that goes to the bolt. The other 86% is just reducing and increasing and reducing and increasing the clamping force. All right. So what is the preload? Well, according to our book, for permanent joints, we want the initial force to be about 0.9 times the area times the proof strength. All right, and I looked up the proof strength. I know the area. So this means my proof strength here is, or my preload is 10,850 pounds. Wow, 10,850 pound force. Right now, remember, my bolt is only good to about 12,000 pounds, 13,000 pounds, and I'm going to use 10,000 of it. I'm going to really, really load this thing up before I apply, my separating force. So again, I know that my median force, Fm, equals, it's going to take all of the preload, right, plus the force that I apply, F max, over 2, right? Why is that? Because it's this, it's going to look like this now. Right, so this is my preload up here, and then I've got some alternating fraction of that. But I've got great news, right? And my great news is, I'm going to go back to green for this, it only gets 14% of this, right? All of the preload, but only 14% of that. I go back down here to figure out my alternating load, and that is, the alternating load is just this part. It doesn't require it doesn't depend on the initial load. So that becomes, again, F max. Remember, F max is my separating force divided by 2. But again, I've got the same bit of good news here, that this only gets 14% of that. So now it just becomes a bit of an algebra fest. Let's see, I've got to go for a safety factor of 1. Let's go like that. For n equals 1, using Goodman, I know that, let's see, it's the alternating force over the endurance limit, and I know the endurance limit. The alternating force is 0.14 F over 2 over SE, right? Plus, let's see, my midline force, or my mid-range force, or my mean force. So that's Fi plus 0.14 F over 2, and all this goes over my ultimate tensile strength, and that now has to equal 1. Now the algebra here is kind of leads us to some insights. Well, I'll just do a little bit of it, so we can clean this up a little bit here. So it's 0.14 over 2SE plus 0.14, or F, plus the same deal here, 0.14 over 2SU F equals 1 minus F initial, my pretension, over my ultimate strength. Okay, so what does this mean? This is the same as I did the last time, right? This looks really the same, except for 2 things. I only take 14% of it, and it's 1 minus the fraction of my pretension, or the ultimate strength. So normally this would be 1 over n, right? I'll put this over here, 1 over n. And so by reducing this by taking 1, reducing it by this fraction, I've already got some small number. It turns out this works out to be about 0.3 something. So I've already kind of gained a safety factor of 3, right? Now I go through this whole thing. If I solve for my F max, right? Anybody have a guess what I get? 11,850 pounds. Holy cow. So by pre-tensioning the bolt, right, I've drastically changed, right, how this whole thing works. So if I were to go up here and sketch this on a Goodman diagram, let's draw Goodman. Where's my thing here? That's good. Let's do it over here. And so I know my Goodman goes roughly from here down to here. So let's label this stuff. Because we've got all these plots, we forget what's what. This is sigma alternating. This is sigma mean. This is the endurance strength. This is the ultimate tensile strength. I should probably put some a yield line in there. But before, my mean and my alternating stresses were really the same. So I was operating at about here. So let's go. Whoop, I need this. I'll do this in red. So mean and alternating stresses were the same, remember? So I was operating at about here. So this, what was this again? This is no preload. Right, but when I could, when I added a big pre-tension, I actually operate way over here, and so I can get the same amount of life. So let's do that in green. And we'll go back to here. This isn't turning out to be as... The Goodman diagram isn't as useful as I thought, but it's something like this. And that is preload. But the net result here is that our alternating stress has to be low, but the clamping force picks up a lot of it. Right? So hopefully this is compelling, or at least enlightens you as to why preloading the bolts is a big deal. Using big, over-spec'd bolts and then not tightening them is bad. Right? We want the bolt just strong enough so that it can be stretchy, and by pre-tightening, we protect the bolt and let the joint do most of the work. Okay, enjoy that. That's it for your Monday lecture, and enjoy the discussion problem on Tuesday.